Item number 8.1 is a presentation regarding the Great Lakes water level forecast, and we'll get Aisha to introduce our speaker.
Thank you. So we have a guest speaker today, Frank Seglenieks. So I'm getting that last name right. He is a water resources engineer with Environment and Conservation Canada, has been since 2009. And he's authored numerous publications regarding various hydrology aspects, and particularly around the Great Lakes. So he's here to talk to us today about the future climate and Great Lakes water level projections.
Okay, hopefully you can all hear me.
Yep.
Thumbs up, yes. Okay, good. You know, you never know microphones and Zoom meetings and all. Yes, like I said, I was introduced Frank Seglenieks. I work out of the Canada Centre for Inland Waters down in Burlington, Ontario. And Environment and Climate Change Canada. Obviously, it's a team effort. So those are the various people who have helped me out on my team. So if we go to the next slide. So this is the outline of what I'm going to talk about. Lately, I've just been putting the take-home messages right up front and saying, you know, these are the most important things to remember from the talk. And then the rest of the talk is just kind of justifying everything that I've done in the take-home messages. So, and then a review at the end. So we're going to start with the take-home messages right now. So click once. We'll make it turn red. Go red. So next slide. And then next slide again. So first take home messages. I hope you can see that well. It's still a bit tough on my screen. So what this is showing is the measured Lake Michigan Huron water level for the measured for a little bit of 100+ years, go up to 2020, just because that's where the study was there. And then on the right side, again, hopefully you can see it on your screen. It's a little bit faint on my screen. Are just the different projections, and you've heard of this change in global mean temperature, perhaps, that the Paris Climate Accord is trying to keep the change in global mean temperature less than 2 degrees, even some trying to get it less than 1.5 degrees. But the take-home message is that when we project these water levels out to the future, we see more extremes, both on the high and the low end. So it's not just a question of flooding, it's actually a question of drought as well, or more likely. And as you get higher change in global mean temperature from 1.5 to 2 to 2.5 to 3 degrees, you can see that range just keeps expanding and expanding. So that's message number one. Next slide. The next one is that these are projections. So we're not saying that in the year 2045, we're going to have a high water level. What we're saying is that it increases the probability. So you can think of it as one of those big lottery drums with all the balls inside of it. So on the left side, left side, I think it's left side for you as well. We have the current climate. So you can imagine maybe there's 99 of these green balls, and one of these is a red ball, and that red ball represents an extreme water level. Maybe it's a water level that's very high, let's say. So in the current climate, we only have one of those red balls, and then every year, just one of these balls just comes out. Now, what we can say is that in the future, as we increase the global mean temperature, well, with 1.5, maybe we add one more red ball. 2, we add a couple more, and 2.5, and still go back there. 2.5, we're still adding more red balls. So, but even under 2.5, it's still a random process. So you could still be pulling out green balls year after year. So it's not going to say that 100% for sure we're going to see these extremes. It's just that they become more likely the further you go into the future and the more that the changes in global mean temperature. Next slide. And what was really going to happen is going to depend, of course, on how society acts. We can't say in 50 years, will we have, has society changed its emissions of greenhouse gases, and will that reduce the warming to less than 1.5 or 2, or will it go up to 2.5? Just some random headlines I've pulled out, 2 degrees, 1.5 degrees. The top right one there in Forbes, that's actually just from a couple days ago. I mean, there are some studies that say there's a 50-50 chance that we're going to get to 1.5 within 5 years. So that could even come up faster than we thought. So it all depends on, again, how society reacts, and then how the atmosphere responds to those changes in the global mean temperature. So those are the big messages of this talk. Now I'm going to kind of go into some background and some more detail on how we got there. So next slide. Background, and here's the next slide. Just to get it straight, we consider, we always talk about Lake Michigan Huron as one water body. I know, politically we split them up. So we consider the Lake Huron, Lake Michigan, and Georgian Bay all just to be a single water body. Michigan and Huron, the Straits of Mackinac, obviously Lake Huron, around Manitoulin Island and the Bruce Peninsula. There's enough of a connection hydraulically that although there might be local, influences, the wind, or maybe local inflow if it rains in one part of the basin. Well, we're talking about a monthly average. It's going to average out, and the water level is going to be the same in all those water bodies. So we just consider it one water body. So when I say Lake Michigan Huron, yes, that's also applicable to Georgian Bay. So all of this is just one water body. Next slide. And just a brief background, there's something called the IPCC, International Panel on Climate Change. It gets into the news. They release these big studies every 6 to 8 years. You can see the ones that were there. Unfortunately, there's a new study that just came out last year, the assessment report number 6, but it takes a few years to actually get all that data together and process it and get the final result. So just be aware, this is from the data from the 2014 study, but rest assured, we have started looking at the 2022 data, and eventually we'll do comparisons, but we're not at that stage yet. Next slide. And the reason we do it, again, getting a bit into the weeds here, is that when they say that the data is released, we get what are called GCMs, global circulation models. And you can see on the left there, that's the resolution we're talking about, maybe 200 kilometers. And you can see in the middle of North America, we don't actually see the Great Lakes at that resolution. So we have to do we have to downscale, what's called downscaling the data to regional climate models, which have resolutions anywhere from 20 to 40 kilometers. And there you can see on the right, when you're looking at that scale, well, now you actually see the Great Lakes. And of course, if you can't see the Great Lakes, if you can't see the actual lake surfaces and you're trying to model the climate and the weather, you're just not going to get very far. So we have to wait for these RCMs. And again, those take a couple of years, and then we do other processing. So next slide. And then next slide. So although I'm concentrating mostly on the lake levels, because that's what the theme of my talk was going to be, I'll just do 2 slides here. We also look at what's happening on the land surface, because it's all connected, of course. So you can see that, air temperature, you can see that those are increasing, projected to increase under climate change. And then next slide. So when we're talking about precip, we're also seeing that precip, it has the projection is to increase, but you kind of lose a lot of detail when you say, okay, it's going to increase on an annual scale. So just let's concentrate on the left side. There's a lot to this graph, but just on the left side, you see the change in precipitation. So any bar above 0 is an increase in precipitation in the future. If it goes below, then it's a decrease in precipitation. And you can just see that in general, we're seeing more of an increase in the winter time and early spring of precipitation, but in the summertime, maybe no change, or even like in August, actually a reduction in the amount of precipitation. So we have to keep that in mind. Although there's a general increase in precipitation, seasonality is really there. So, when I talk to conservation authorities who have to manage dams, maybe they have to take this more into account, that they're going to be getting more, odds are they're going to get more water there in the winter and the spring and less in the summertime. So how you manage, your reservoir could be affected by that. So we have more details on this in a journal article at the end of the presentation. I have some links to it. So that's all I'm going to say about the land surface. Next slide. We'll move to lake levels, which is what this talk is mostly about. Just the way we go from these climate models that are around the world, then we just focus in on the Great Lakes. We put it through something called the Coordinated Great Lakes and Regulation Model, and we get these water level projections. So next slide. Just kind of says this in words. So we use this coordinated routing model. It takes the water and the thing you really need to do when you're looking at the lake levels is those connecting channels. So, in the case of Lake Huron, of course, you got the St. Clair River and the Detroit River, which gets you into Lake Erie, the Niagara River, and all of those. The thing is that now when we go into some climate change scenarios, we get into some really extreme situations, like water, a lot of water coming out of Lake Huron going down the St. Clair River, for instance. So some of the assumptions that these models were made on could be violated when you start talking about that. And we recognize that. So we're looking into, okay, what would actually happen in these rivers if there was such high water volume. So again, these are, projected water levels that we're going to, but, you know, we're not saying that to this exact centimeter, this is where the water is going to go, but it just gives you an idea of, you know, where the projections lead us. So next slide. And then this is similar to the graph. I'm just going through the different lakes here. So starting out with Lake Superior has less of a range. So the y-axis on this, the range is always going to be about 5 meters on all these graphs. So you can compare them relatively with how much variability we've seen. So, I mean, Lake Superior, a little bit of a change as you go. So next slide. One that you're most interested in, Michigan Huron, has more of a wider variety. Always get questions about why Michigan Huron has such a wide variation. Part of it is the question of why Lake Superior has such a low variability, and part of that reason is that it doesn't have an upstream lake. So the range and variability of Lake Michigan Huron is partly the upstream lake. So you have Lake Superior coming in. That's going to change some things, and also just it's such a big basin. You see that if you I know Lake Superior is the biggest lake, but Michigan Huron, if you take it as one lake, is actually the biggest lake, and of course has the biggest land area associated with it. So kind of those factors give you more variability, and going to get more into detail. But as I said at the beginning, you just see that as you get higher changes in global mean temperature, there's projections for more extreme lake levels. Next slide. Just a similar story on Lake Erie. A little bit less of a range, but you see that same pattern. And next one is Lake Ontario, and that has some spikes because there's a regulation plan. I won't get into it. So there's a regulation of how much of the outflow of Lake Ontario, so that affects the future projections, because there's a little bit of control on that. So next slide. So if we took all those different models and different spaghetti plots and put them into these what are called box and whisker. So it just kind of shows you where most of the data is. And two things, obviously, you can see Lake Superior has the lowest range. Michigan Huron has the largest range, but so do the other lakes downstream. And also, again, just the change in, as you get higher changes in the global mean temperature, you get more extremes. You can also see on each one of those boxes, there's a red line, and that's the average level. So you can see relatively the average level doesn't really change all that much, even when you're talking about going into the future. It generally is going up, but we're talking 20 or 30 centimeters, not that big. But of course, it's not the average that's going to cause you problems as far as flooding or low water situations. It's those extremes that you have to think about. So if we put numbers to it, next slide. And so if I just concentrate on the left side of the graph, you can see, so percentage exceedance. So, you know, the 1% exceedance up there is like, that's the highest water, that's the water level you expect to see like 1% of the time. So some people call that 1 in 100 years level. It's not the best wording, but you can kind of think of it that. So 1%, and then 99% is like a low water level. And so 50% is the average. And so you can see that with the changes in the global mean temperature between like of 1.5 degrees, let's just concentrate on that. You can see the 1%, that 1 in 100 year level goes up from 72 centimeters above the average to now 1.14 meters above the average. So, you know, 42-ish centimeters. And you can see that level gets higher as you get into higher and higher changes in global mean temperature. Just a note there, the first note is that I made a mistake here. It should be since 2020, since 2000, sorry, since 2000, not since 2020. That was my bad on that one, because when we were doing the study, we used a reference period of 61 to 2000. But so it's interesting to note that in 2013, Michigan Huron actually had its lowest water level ever recorded, a monthly water level that would have been minus 1.1 meters less than the average. So again, it would actually be below this level. And the highest one was just a couple of years ago in July of 2020, where it got to 79 centimeters above the average. So again, it would have been up here. So if we were to redo this from measured to 2020, these numbers would even be greater, but this is the reference period we use, so we have to use these numbers here. So you know, maybe we're already starting to see those effects of, you know, a changing climate. We're starting to see even we've seen higher extremes than we have, you know, in the measured period going up to 2000 in the past 20 years as well. So, so that's it. Next slide. And now just going to review these take-home messages. So again, as I said, beginning, more extremes in lake levels, both high and low. That's the important part. Both high and low are projected into a changing climate. The extremes are more likely, but not a certainty, and it will depend on how society acts in the future. And then on the next page, I have questions, but I also have a link to those 2 journal articles. I'm assuming everybody will have access to this presentation, so hopefully you don't have to copy down all this stuff and that it can eventually go there. But the first one is about lake levels, is a journal article in that Great Journal of Great Lakes Research, and then it's more about the land surface is the second paper. Just they're too long to have into one paper, so of course we split it up into 2. So that was my quick rundown of many years of work. So hopefully it was quick. And again, if you want details, I mean, both those articles go into much more detail than I can do in this 10-minute presentation. So.
Thank you very much for the presentation. Really appreciate it. We'll open the floor up to questions, comments. Eric.
Thanks. So Frank, great presentation. Obviously, the concern here is to do with the lake level. So obviously, the lake level is determining the extremity or the extreme on the climate side. The lower it goes, the lower, the higher temperature of the bay, and then it rebounds back up if the lake's a lot higher.
Sorry, I don't know if I understood the question.
So the question being, if the lake level was stable,
yeah,
the temperature would not change as great.
Do you mean the temperature of the water?
Yeah, isn't that what you're comparing, or no?
Well, no. So when I had those changes in temperatures, those are the changes in the global mean temperature. So like the temperature all around the world.
Okay, I'll
Sorry.
backtrack.
Sorry for that misunderstanding. It's just that in the news you hear a lot about Paris Climate Accord trying to keep the changing global mean temperature under 2 degrees or 1.5 degrees. So I was trying to put it into those kind of terms.
Okay, well, I understand now. Thank you, Frank.
Okay. And we do no, not in the paper, but I mean we do look at the change in the water temperatures as well, because that's part of the equation. Didn't get to it here, obviously.
Thanks, Barry. Thanks, Frank. Brian, I saw your hand.
No, I was just requested to raise my hand when voting, and I don't have the feature here. So I'm sorry. Go ahead.
So I was just something that I could share, and maybe Frank can comment on, but in Tiny Township, we've been battling those extremes with the highs and lows of Georgian Bay. I'm sure everyone has to a certain degree. The previous council has asked for a shoreline alteration bylaw. Basically we've engaged AQ5, which is a coastal engineering company, to consult on what exactly that means. But we're looking at shoreline resiliency versus hardscaping is one of the things that we're talking about. Preserving some of the natural heritage features down there, so tree cutting bylaws, that kind of stuff. Our first report's not scheduled until the beginning of second quarter, but definitely be willing to share that with everyone here. Maybe useful. And I guess my question to you, Frank, is have you seen any great shoreline alteration bylaws or similar kind of things that we should be implementing?
Not to that level of detail, but I would say it would be important for these plans to consider higher lake levels than we've seen before. So like whatever, bylaw, I mean.
So the 178 meter line is no longer the line?
Well, I would say consider what we have put out here as far as changes. I can't think of the exact numbers right now. So, and again, it's your risk tolerance. So you're talking about 1 in 100 year, 1 in 500 year, what kind of risk you're looking at. So I would say just make sure you consider that what you've seen in the past is not what you're going to see in the future. Most likely that they're going to see even more extreme. So I wouldn't base it like from don't take the water levels from 1961 to 2000. Say, well, I mean, at least to 2020, but then even go beyond that and just say, yes, this has a high probability of happening. And the other thing, I mean, getting a bit more into the weeds, is lower ice cover. So it was a winter, about 3 winters ago. I mean, it's kind of like it is now. I'm not sure. I think there is a little bit of shore ice along some of the bays in Georgian Bay, but a couple of years ago we had a winter where there was absolutely no ice, like even along the shoreline. And then we'd have and the water level was high. It just happened to be at the same time. So when you had that wind energy coming in with the waves, even if you don't have lake ice all across the lake, if you have it in that last 5-10 meters, that's going to absorb a lot of that energy. But in the future, if we don't have that shore ice like we did a couple of years ago, now that energy is just hitting your shore, and it's like that full energy is hitting the sandy beach, or I mean more about the east coast of Lake Huron, because the sand dunes was more where we got more reports from. But there was just a lot of erosion that year, and it wasn't particularly windy or anything. It's just that there wasn't that shore ice to absorb to take up that energy. So just something else to consider. I don't know again how much into the weeds that report would go into about considering ice on the lake. So kind of a complicated answer. Sorry, but something to consider.
Thank you. Going around the room, looks like we're good. Appreciate your time, Frank. We're going to move by Mark, second by Danielle. The SSEA Joint Municipal Service Board receives Environment and Climate Change Canada's Great Lakes forecast as information. All those in favor? Brian, you good? Good. Man, carried.